Good morning. This is our fourth unit, Metamorphic Rocks. We have changed textbooks a few times, so I think this is chapter 5 or 6 in the Marshak book. Anyway, this is the second unit for your second exam. This is a very quick unit, and for our hybrid semesters, we will spend probably less than one whole class period covering this chapter, but we will go ahead and narrate all the slides, or most of the slides, for you to look at this on your own time through Canvas. So what are we looking at here for our opening slide? Well, here we see some geologists probably on the side of the road, and they are looking at metamorphic rock. Okay, so we can tell a lot about this rock just from looking at a picture of it. First of all, do you guys see any layers, any color banding there? Yes, hopefully you do. And are those layers just necessarily horizontal or flat lying? And the answer is no. They are convoluted. They are kind of folding back on one another. What does this tell the geologist? This tells the geologist that this is a myelinite gneiss. Okay, so the parent rock here was likely granite. It is a metamorphic rock. It's a high-grade metamorphic rock. It was metamorphosed at a depth greater than 12 to 16 kilometers, and it was likely part of a shear zone, or meaning part of a fault plane. And how do we know that? Just from looking at how these color bands are wavy. Okay, metamorphism. What is it? You need all three bullets here in your notes. As always, I expect that you are actually taking notes while you are listening to and watching the narrated PowerPoints. It takes the place of class time that we just don't have much of anymore. Okay, so metamorphism is the process by which pre-existing rocks are altered or changed. So if you think back to the rock cycle that you learned not only in your 9th grade earth science class, but you probably learned about the rock cycle back in grade school. Rocks don't necessarily stay the same. All right, so rocks can be metamorphosed, changed into something else, perhaps even a whole new mineral assemblage. Second bullet there is very important. Where do metamorphic rocks form? They don't form just anywhere. They form in the lower portions of the crust only. This is a good time to review. Where do sedimentary rocks form? The upper crust. All right, sedimentary rocks form in the upper crust. Why? Because that's where weathering is occurring. Metamorphic rocks are forming in the lower crust. Why? Because that's where you have enough heat and pressure and perhaps differential stress to cause those metamorphic reactions to occur. All right, so if metamorphic rocks have been changed or altered, that means they used to be something else. Okay, so each metamorphic rock has a parent rock, also known as a protolith, just simply meaning the rock it used to be. Here are some examples. Well, you need to know some examples for your second exam. Yes, of course you will. Okay, so sandstone is the parent rock of quartzite. So quartzite is metamorphosed sandstone. Limestone is the parent rock of marble. So just as limestone will fizz and dilute hydrochloric acid, marble will as well, because it is simply recrystallized calcite. And then shale is the parent rock of slate. There's a couple other ones here that I will write on the board on our day in class, but let me go ahead and mention them for the people that end up in quarantine or in case we go online before them. Gneiss, G-N-E-I-S-S. Gneiss is a type of metamorphic rock, and gneiss has at least a couple of different parent rocks. Oh, excuse me. Allergies. My cats like to sit near me when I'm working on the computer. Okay, so back to our metamorphic rock called gneiss. What are parent rocks for gneiss? Well, shale is a common parent rock for gneiss, but granite is also a common parent rock for gneiss. So more than one parent rock can become banded gneiss. Some examples here. On the left, you have sandstone, the parent rock. On the right, you have the quartzite, the metamorphic version. So the sandstone is a sedimentary rock, and it has good porosity and permeability. But the quartzite there on the right is recrystallized quartz, and so the quartz grains are locked tight together, so you lose your porosity and permeability there in the metamorphic process. Here we are looking at a fossiliferous limestone on the left, and then a marble outcrop there on the right. So that limestone is really cool. So you see a lot of fossils there. All right, so you see the things that look kind of like dog bones. Those are bryozoans. And then you see some brachiopod shells. And you see the things there that look like buttons. It look like somebody took buttons off a shirt and then just dumped them on the rock there. Those are pieces of crinoid stems. If you want to learn more about crinoids, come back and take Earth history in the spring. Okay, so in the bottom right, we are looking at the corner of a marble quarry. And look, somebody was kind enough to kind of clean that off before they took a picture of it. Certainly, marble is prettiest when you're looking at a larger piece of it. So either at the marble quarry or a marble countertop. In class, when it's not COVID, I pass around hand samples of marble, and while they are cool to look at, they're just not as pretty as when you see them on a bigger scale like this. Why? Because you can see all the color bands in it. And here we have shale, the parent rock, in the top left, and slate, the metamorphic rock, in the bottom right. I just love slate. It's one of my favorite rocks. It's very useful. It's very pretty. It's a lot stronger than shale, so there are a lot of neat uses for slate. And the colors can vary. We see here we've got gray slate, slate that's red, slate that's almost purplish, slate that might be more of a greenish color. Shale can also form something called garnet mica schist. So in class, I would pass around the garnet mica schist and let everybody get a look at the pretty garnets in it, but that will not happen either when we have COVID or when this is a fully online class, which happens in the summers. All right, so shale there on the left is just your common sedimentary rock. It's basically just clay minerals smushed together, making their own mud cement. But the garnet mica schist there in the bottom right, notice that's very different. That rock looks a whole lot different. So what are we looking at there? We're looking at a lot of micas, muscovite and biotite, sheet silicates, and then garnets as well. It's one of my favorite metamorphic rocks. Okay, so you need to know both these bullets here. All right, so what is metamorphism? What does that really mean? How does the rock change? So metamorphism refers to solid state diffusion. Okay, so diffusion is talking about atoms migrating. In this case, they migrate slowly through a solid. That's why it's called solid state diffusion. Now, there is no melt involved. If this rock melted, then it would form an igneous rock, not a metamorphic rock. So the fact that the rock remains solid throughout all this, and why does that happen? Because of pressure. But what happens is that one by one, you'll have one atom break a bond, migrate a very tiny distance, and make a new bond with an adjacent atom, perhaps changing the chemical composition. Okay, you don't have to write this down. This is basically what I said on the previous slide. So how does this happen? Well, heat is involved in metamorphism, and the heat is not allowing for melt because there's too much pressure. But heat does mean that the atoms will then vibrate. And that's going to cause bonds to become bent, stretched, compromised, and occasionally here and there broken. So the atoms migrate and bond with an adjacent atom, which might give you a new chemical formula, therefore new minerals. The agents of metamorphism, you need to know these for your second exam. This is a short answer question, I believe. Short answer or multiple choice, one of those. Anyway, you really just need to know what's underlined, not the rest of it, but we will discuss all of it. So heat is involved. So where is that heat coming from? Well, it could just simply be the geothermal gradient, which we discussed in a previous unit. Remember, an average increase in temperature of 25 degrees Celsius for every 1 kilometer of depth. Or it could be that there's an igneous intrusion nearby. If you have the right tectonic setup or a hotspot volcano, you're going to have melt produced. So you can get high heat in relatively shallow settings if there's an igneous intrusion nearby. Second bullet there, pressure, which just refers to the weight of overlying materials. Rocks in the subsurface are under pressure. We could think of this as confining pressure or confining stress. So the first two bullets there will always be present in metamorphism. And, how much they're present can vary. It could be low heat and low pressure. It could be high heat and high pressure, something in between. The last two bullets may or may not be present. So, bullet number 3, hydrothermal fluids. Excuse me. Hydrothermal fluids. This just refers to heated groundwater. So hydrothermal fluids are especially likely to be present if you have a magma chamber nearby. And what's cool about the hydrothermal fluids is they're basically responsible for changing limestone into marble. Differential stress is another possible agent of metamorphism that may or may not be present, and we'll talk about it more later. Just some examples here of pressure. You don't have to write any of this down. So the average atmosphere at Earth's surface is 14.7 pounds per square inch, psi. We could also refer to this as 1 atmosphere, the average air pressure at Earth's surface, at sea level generally. So 1 atmosphere could also be expressed as 1 bar. So in meteorology, we represent pressure in millibars because we are generally talking about low pressure systems like hurricanes. So you'll see us in meteorology represent air pressure in millibars, as in you're cutting that bar into smaller pieces. As a matter of fact, at the time that I'm narrating this PowerPoint, which is fall of 2020, the year that just wouldn't go away, there are currently 2 tropical storms, which may become actual hurricanes, but they're named storms. We have Laura and Marco that are about to hit the Gulf Coast basically at the same time. Yep. No, there's no such thing as climate change. Haha, just kidding. Anyway, so in geology, when we're looking at pressure, we need to multiply those bars. So we're going to talk about high pressures, but try to keep our numbers low. So we're going to express pressure in kilobars. So 1,000 bars equals 1 kilobar, just like 1,000 meters equals 1 kilometer. So in this image here from a textbook we don't use anymore, what you're looking at is, of course, this is a shallow offshore marine basin, and we're just simply looking at layers of materials, sediment, that are building up over time and slowly changing into, say, solid rock, sedimentary rock. So where that white arrow is pointing, they're basically just saying that the further down you go with depth, you have increasing pressure. We could think of this as confining pressure or confining stress. And then the image there on the bottom right, notice that the arrows are all the same size. That is just telling us that in the case of confining pressure, the pressure is equal in all dimensions that the squeezing is occurring. In other words, you don't have the pressure greater in one direction than another. Can that happen in some instances? And the answer is yes, it can, and we will look at it later in this unit. Examples of pressure and depth. All right, just some examples. No, you do not need to know this for your second exam. At a depth of roughly 40 kilometers, which is about the average thickness of continental crust, we expect to find about 12 kilobars of pressure, or 12,000 times the pressure we are experiencing right now. At a depth of between 80 and 100 kilometers, which is roughly about the average thickness of an oceanic plate, the whole plate, we expect to find 29,000 kilobars of pressure, or 29 kilobars of pressure, or 29,000 times the pressure we are experiencing right now. Hydrothermal fluids. You would need to write down these first two bullets here. Okay, so hydrothermal fluids. What do? Well, they accelerate metamorphic reactions. So basically, hydrothermal fluids act as a catalyst in metamorphic reactions. I used to have that word in the exam question here, but too many students didn't have a clue what catalyst meant. So I've taken it out of the exam, but the hydrothermal fluids do act as a catalyst, meaning that they can start the metamorphic reactions going, and they can accelerate them, make them go faster. So hydrothermal fluids play a large part in changing limestone into marble. That third bullet there, you don't need to know for your second exam, but hydrothermal fluids may produce veins in a rock. I'll show you a picture what this looks like. So what does that mean? It means that we have rocks, and they have fractures in them. Remember, in the previous unit, Sedimentary Rocks and Weathering, we discussed the formation of joints or fractures in the rock. Well, this can happen not just at the surface, but in the shallow subsurface. I think we mentioned in the previous unit as well that weathering actually begins in the shallow subsurface. It's not just at the surface. So you can have a rock that is still buried to some shallow depth, and it has fractures in it. And then if you have even slightly heated groundwater that has calcite dissolved in it, that groundwater will tend to migrate into those fractures, and calcite, or it could be quartz, will grow out of the groundwater into those fractures and permanently leave this mineral behind. So here are a couple of images. The image on the right is not the best, and I say that only because it actually it might look like mud cracks. It's not, it's actually veins, but we'll just leave that one alone. The one on the left is a little bit better. So you're looking here, they're taking a picture, kind of looking up, the side of a rock outcrop. You see the sky there at the top, and then you see that the rock is mostly gray. Perhaps that is some kind of mudstone. But what you see there that looks different is you see that white material kind of snaking through. Those are veins. That is likely either quartz or calcite. Okay, so we're going to discuss differential stress now. So during metamorphism, rocks may be either compressed, squeezed, or stretched unequally in different directions. We refer to this as differential stress. You're going to need to know the two different types of differential stress for your second exam, normal and shear. And this will be in the form of matching. I will have the drawings there for normal and shear stress and ask you to be able to match them up. But before we look at the drawings, let's describe these a little bit more. Okay, so normal stress is either compression, squeezing, or tension, pulling apart, perpendicular to a rock layer. And we are going to just focus on the compression or the squeezing. So in the case of normal stress, your rocks may be squeezed greater in one direction than another, and you're going to apply these forces perpendicular to the rock layer. Shear stress is a little different. Shear stress is still a type of differential stress, meaning that you are going to squeeze or push greater in one direction than another. But in the case of shear stress, the forces are applied parallel to the rock layer. So you can kind of think of it as one part of a rock layer or a mineral crystal being moved relative to another. Perhaps in the case of mineral crystals, giving you more of a rhombohedral shape. Okay, so some drawings here. So the drawing on top is a little bit better. That, of course, is showing shear stress. So let's say that this is a rectangular feldspar crystal in a granite, and that granite is being metamorphosed. And that rock, as it's undergoing metamorphism, is caught up in a mountain building event, and you have shear stress applied. So what you can end up with is that the feldspar crystals in that rock have more of a rhombohedron shape than a rectangle shape. Okay, now looking at the bottom. So in the bottom, let's say again, maybe we are looking at feldspar crystals in a granite, and that granite is going to be subjected to normal stress. So notice the size of the arrows there on the left. They are bigger moving in from the right and the left. That just simply tells you that you're going to squeeze greater in that direction. So I'm not super happy with the drawing on the right there. There's not necessarily a ton of these drawings out there. So it doesn't necessarily end up looking like a dumbbell. It could just end up looking like an elongate rectangle. These are our two different types of differential stress. Okay, I was going to skip ahead and show you a photo of a stretched pebble metaconglomerate, but that must be later on in this presentation. So we'll get to it when we do. Okay, so this is a pretty good drawing from a textbook we don't use anymore. And up there in the top, you see something that should look familiar. We looked at it on an earlier slide. So you are basically collecting sediments in that shallow marine basin that will lithify and form sedimentary rocks. And in this process, and they might eventually become metamorphosed as well, in this process, it's under confining stress or confining pressure, just meaning that those purple arrows there are all the same size. So you're being squeezed equally on all sides, just as somebody who is scuba diving, when they are scuba diving in the, I don't know, 20, 30 feet of ocean water, they are experiencing hydrostatic stress, and the pressure of that water is pushing on all areas of their body equally. Now, in the image there on the bottom, that's actually a really good image. That's a great way to show differential stress. So what you see there is a mountain range. Okay, and how do mountains form? Well, we're going to get to that when we get to plate tectonics, which will happen after our second exam. But notice the red arrows there moving towards each other. What we're showing here is some kind of convergent boundary, squeezing. So what happens here is that those rock layers that had been undeformed and just flat lying, horizontal, are now all convoluted. Okay, so this rock has been subjected to, well, it's buried in a mountain range, so it's under heat and pressure, but it's also being squeezed greater in one direction than another. That's differential stress. So you end up with deformed strata like you see there on the left. So that's generally your differential stress is going to occur either in a mountain building event or along a fault. Here is another version of a similar drawing there. Okay, so here we are taking a look at a parent rock on the left. This is called granodiorite, which means it's halfway between a granite and a diorite. You might remember from igneous rocks, the second unit we did, that granite is felsic and diorite is intermediate. Anyway, it looks very much like a granite, and you see there that there's no pattern on that rock on the left. There's no pattern to the colors or the minerals. Randomly oriented mineral grains. But over on the right is what that rock can become if it is subjected not only to high-grade metamorphism, but differential stress. So you end up there with banded gneiss, which is a high-grade metamorphic rock, and you end up with your, so not only do you have layers, compositional banding, notice you have light and dark, light and dark. So basically what happens here when you're forming banded gneiss is that the felsic minerals all come together and the mafic minerals all come together. But then we also know that this is subjected to differential stress. That's why those color bands are not just horizontal flat line, okay? They are now convoluted. Okay, so All right, so we're kind of introducing a question here that's, well, we've talked about this already. I think we talked about this back when we did igneous rocks. Okay, so metamorphism is occurring at depth. It's in the lower portions of the crust. So there is heat involved from the geothermal gradient or from a nearby igneous intrusion if you have one. So why is there no melt? Okay, so you have greater temperature at greater depths. And here's an example. At a depth of 20 to 25 kilometers, which is really just not all that deep within the subsurface, the temperature could be 500 degrees Celsius just from the geothermal gradient alone. So that might almost be hot enough to melt quartz, but you don't get melt. Why not? Because of pressure. All right, so what happens here is that these rocks in the subsurface at increasing depth, not only are they subjected to ever increasing temperatures, but ever increasing pressures, okay? And pressure keeps bonds from easily breaking. So the individual atoms do not easily break free from a mineral's crystal lattice. Okay, if you had atoms breaking free all over the place, that would be melt, but you don't have that. Instead, you have metamorphism, because one by one, very slowly, you have one atom at a time breaking free and migrating and forming a new bond. So metamorphism occurs without melt. Okay, we just need the first two bullets here. So what happens to individual minerals during metamorphism? So there's actually 4 different things, but this is beyond the scope of an introductory class. That last bullet and those last 2 things are beyond our scope, so we're just going to focus on the first 2. So generally you're going to get either recrystallization or neocrystallization. Recrystallization is pretty much exactly what it sounds like. The size, shape, and orientation or arrangement of minerals is going to change without destroying any old minerals or without growing any new minerals. So recrystallization, you might start with quartz, say a quartz sandstone, and that quartz sandstone is subjected to heat and pressure, and it metamorphoses, changes into quartzite. So you're going to change the size, shape, and arrangement of the quartz grains, but you're not going to destroy any quartz and you're not going to grow any new minerals. That's recrystallization. Second bullet there is neocrystallization. So this is the growth of new minerals. Neo generally refers to new. Okay, so the growth of new minerals due to that solid state diffusion process. But if you're going to grow new minerals, you're going to have to destroy old minerals in the process. So neocrystallization, a good example of that would be shale turning into garnet mica schist. So the shale, the parent rock, sedimentary rock, a bunch of clay minerals pressed together, is going to turn into garnet mica schist. How does that happen? Well, you're going to form micas, muscovite and biotite, and garnets. But in that process, you're destroying the clay minerals. And again, pressure solution and plastic deformation. Well, those are fun, but those would be more useful in a structural geology class. Okay, so in this image here, what we're showing is the idealized geothermal gradient. So this is a mountain range. You recognize that thing in the middle at the top. What is that weird thing at the right? That is something called a subduction zone, and that is something that we will learn later in the semester. It's a type of convergent plate boundary where you do produce melt. All right, so going back to that idealized geothermal gradient, you see there that you have increasing temperature with depth. 300 degrees Celsius, 600 degrees Celsius, 900 degrees Celsius, 1200 degrees Celsius. So are you going to have metamorphism occurring? Yes, you will. You also see what appears to be melt and magma chambers. Why is that there? It's because of the plate boundary. That's something that we will get to after the second exam. Okay, so examples. I actually mentioned this on a previous slide, but we could go ahead and write these down. How about bullets 1 and 3? Okay, so a good example of recrystallization would be quartzite. So what happens? The quartzite is still made of quartz, but its texture is very different. The crystals often become, well, they can become larger. Sometimes they can become a little smaller. It depends on the grain size you start off with. But they are definitely changed in shape and orientation, are closer together. Another example that may or may not be written down in the PowerPoint is limestone changing into marble. So limestone, you're beginning with calcite. And then with marble, you basically just have recrystallized calcite. So the marble is made of calcite just as the limestone is. But the marble, you are going to lose porosity and permeability. Okay, third bullet there, garnet mica schist. So this is my favorite example of neocrystallization. Again, you start with shale, which is just clay minerals, and the clay minerals get destroyed in this process, and instead you form muscovite mica, biotite mica, and perhaps garnets. So we're looking at some images here. So bottom left, that is a sandstone. If you're wondering why is it kind of pink, well, that's an Arcose sandstone. I just threw in a different kind of sandstone for fun, and it turns into quartzite, the rock on the top left, if it's metamorphosed. In the middle there, just a typical outcrop of shale, bunch of clay minerals compressed together. And then on the right, you have a nice sample of garnet mica schist. Here we go. Now we finally have that image of the stretched pebble metaconglomerate. So up on the top left is a conglomerate, a typical sedimentary rock, poorly sorted, and the larger grains are quartz pebbles that tend to be rounded. But then in the bottom right, that's a picture of something referred to as a stretched pebble metaconglomerate. So that is a metamorphosed conglomerate for sure, but it's really cool because look at the shape of the quartz grains. They are now elongate like a cigar. They didn't begin that way, they began round. So you've had a change in shape. So not only has this rock been metamorphosed, it has been subjected to differential stress. Okay, you're going to need to know what foliation is. We'll discuss that. Metamorphic rocks will either be foliated or non-foliated. So let's talk about foliation. What does it mean? You're going to need to know which of the agents of metamorphism produces foliation. And I might ask you to know an example of a foliated metamorphic rock and an example of a non-foliated metamorphic rock. So foliation refers to a preferred alignment or arrangement or orientation of minerals. In other words, they're not random. They're in some kind of alignment. Now, second bullet there, very important. Which of the factors of metamorphism must be present to form foliation? And that answer is differential stress. So foliation is going to form in the presence of differential stress. All right, third bullet there. What might it look like? You don't need to write down the third bullet, but this was fun back when we could pass the samples around and let people actually look at them and hold them in their hand. It might look kind of glittery or like fish scales if it's got small micas in it that are all lined up parallel. It might look like a waviness. So there are metamorphic rocks that are non-foliated. And what it means is, well, they're still metamorphic rocks. They have still changed, but they do not have any specific arrangement or alignment of minerals. All right, so how about some examples here? You don't need to write down these texture names. What I would ask you to write down in your notes at this point is this. Examples of foliated metamorphic rocks would include things like slate, schist, also sometimes referred to as mica schist or garnet mica schist, and then gneiss, G-N-E-I-S-S. The G is silent. So gneiss is also a foliated metamorphic rock. So the gneiss clearly has, well, I'll show you some pictures. We've looked at some pictures already. Gneiss has an alignment of minerals. You can tell from looking at it. You have alternating light and dark bands of minerals. Again, the felsic minerals line up together and the mafic minerals line up together, giving you the banded texture. In the case of schist or garnet mica schist, what you have is that you have micas, remember, muscovite and biotite and mica, that are sheet silicates. Well, they're all parallel to each other, kind of lying flat together. That's a good example of how to recognize a foliated metamorphic rock. And of course, a stretched pebble metaconglomerate is also a foliated metamorphic rock. How about some images here? These are actually good images. So on the top left there, you have slate. So you might ask, well, what is it about the slate that shows me that it's foliated? And the answer is it's in layers. All right, over on the right is a rock that was listed on a slide, but we didn't discuss it, and that's called phyllite. So this actually looks like slate, but you have a little bit of waviness, what we might refer to as crenulations, and the phyllite will also look shiny, because in the case of the phyllite, you're starting to grow some muscovite and biotite mica. In the bottom left, that is a mica schist. It's hard to tell whether or not there are any garnets in there. And why is there a Canadian coin there beside it? And the answer is, of course, for scale. So other examples here of foliated metamorphic rocks in the bottom right, that is a close-up view of a stretched pebble metaconglomerate. Up on the top left, that is a banded gneiss. We might think of that as a myelinite gneiss. It's definitely a metamorphic rock. It is a high-grade metamorphic rock. It is foliated for sure, but that isn't just any rock. That is a sample of the Acasta gneiss. So the Acasta gneiss is found exposed at the surface in some parts of Canada. It is the oldest rock on the North American continent, and I believe the age of the Acasta gneiss is 3.96 billion years old. So that sample there is actually in the Smithsonian Museum of Natural History. That's a great museum, and I recommend, if you ever can get to DC and you have somebody to stay with, or you can afford a place to stay and expensive food and beer, it's free to get into the museums, and I recommend going. And of course, my favorite museum is the Natural History, where they have all the geology stuff. So not only do they have pieces of this oldest rock of Canada behind plexiglass, but there are pieces of it out in the hallway, or in the walkway, I should say, and you are allowed to touch it. They also have some meteorites, big meteorites that are out there in the walkway, and you are encouraged to touch the meteorites. It's really, really cool. This is just another example showing the difference between the parent rock and the metamorphic rock. On the left, you have a typical granite. Again, you notice there is no pattern whatsoever to the minerals. They're all just kind of mixed together randomly. But over on the right, you see a pattern. You see felsic light minerals together and mafic dark minerals together, and that is a type of foliation. That shows that that is a high-grade metamorphic rock, and it was indeed subjected to differential stress. So slate, there's a lot of neat uses for slate. I think we've already discussed some. A chalkboard in a classroom is made of slate. A pool table is made of slate, but in some places they might use slate for roofing shingles. I find that to be interesting, but also scary. I guess if I had unlimited money and I bought a house and I could have any kind of shingle I want, I might think about slate shingles, but you know, anywhere where you can get hurricanes, tornadoes, or derechos, anywhere where you can have high winds, I think that maybe slate roofing shingles is a bad idea. Because if an asphalt shingle flies off the roof and smacks you upside the head, well, it's not going to kill you. But a slate shingle, that's a different story. This is a neat image here. This is a slate quarry somewhere. I don't know where. There are slate quarries in North Carolina. This is not one of them. I have been to a slate quarry here in North Carolina. It was called the Solite Quarry. And that was a field trip when I was a graduate student at UNCW, and that was a lot of fun. So we do have slate in North Carolina. Matter of fact, there's a part of North Carolina referred to as the Slate Belt. Slate is one of my favorite metamorphic rocks. It's just so cool. Oh, another use for slate is they make really good stepping stones in your yard or garden. And as stepping stones, they're not going to hurt anybody, whereas roofing tiles, they might. Okay, so metamorphic rocks that are non-foliated, you don't need to write down these textures. I'm just gonna have you write down a couple of examples. Okay, so the two good examples here are quartzite and marble. So quartzite and marble also were our examples for recrystallization, meaning that you begin with quartz and end with quartz, or you begin with calcite and end with calcite. But these rocks are not only recrystallized, they also generally are not subjected to differential stress. So there's not going to be any pattern to the minerals here. So they are non-foliated metamorphic rocks. Here we're looking at quartzites in some museum up in the top left, and then a slab of marble in the bottom right. Anthracite coal. We may or may not have time for me to hold up at the front of class and show you guys. Anthracite coal, it looks like bituminous coal, but not exactly. It's shinier, it's prettier, it's less dirty. It doesn't leave stuff on your fingers. It's basically a metamorphosed bituminous coal. So in other words, bituminous coal is the parent rock to anthracite coal. And anthracite coal is considered to be a non-foliated metamorphic rock. It kind of looks like obsidian volcanic glass, but it's very different. Okay, metamorphic grade. I would write down bullets 2 and 4. So not all metamorphism is the same. There are different grades of metamorphism depending upon the amount of heat and pressure involved. All right, so if you have low heat and low pressure, that's going to give you a low-grade metamorphic rock. I might ask you to know an example of a low-grade metamorphic rock. Slate is the perfect example. We're going to skip intermediate. I mean, a good example of intermediate would be mica schist, but I'm not going to ask you that on the exam. But I might ask you to know an example of a high-grade metamorphic rock, gneiss with a silent G. So when you're looking at a banded gneiss sample, just know that that's a high-grade metamorphic rock. It was subjected to high heat and high pressure. Okay, some examples here. On the left, you have shale, a parent rock. On the right, you have a low-grade metamorphic rock it turns into, slate. So in the case of the parent rock shale, it's just clay minerals. They're relatively aligned. In the case of the slate, not only do you have some clay, but you've lost some of the clay and you're starting to add a couple of micas, chlorite and perhaps muscovite, but mainly chlorite. And you'll notice that they are aligned a little bit better. They're perfectly parallel to each other. So that's a type of foliation. On the bottom left, I think we've seen that before, that is the granodiorite, looking very much like a granite. There's no pattern to the minerals whatsoever. On the right is the metamorphic equivalent, and now you have a high-grade metamorphic rock that has also, in this case, been subjected to differential stress. Okay, so we mentioned earlier in this presentation that gneiss, banded gneiss, can have at least a couple different parent rocks. Actually, there's a few parent rocks it can have. We'll just discuss shale parent rock versus granite parent rock. So how can you tell the difference? Well, they'll look different. And of course, cutting thin section slices of them and looking at them with a petrographic microscope certainly helps. So this is a granitic gneiss, meaning that it's banded gneiss, it's a high-grade metamorphic rock, and the parent rock was granite. And you can tell from looking at it. I mean, it looks like granite, doesn't it? Except that you have light minerals together and dark minerals together in alternating bands. Now this is also banded gneiss, but boy, this looks a whole lot different from the rock we looked at on the previous slide. So you still see the alternating color bands, light and dark, felsic and mafic, but I want to call your attention to those wine-colored rounded features there. Those are garnets, relict garnets, meaning left over. Okay, so this is a sample of banded gneiss that had a shale parent rock. So a shale gets buried enough in a mountain range that it's eventually going to turn into banded gneiss. Somewhere along the way, it's going to turn into garnet mica schist. And what has happened here is that the garnets have not been destroyed. And of course, the quarter is there to act as scale. Okay, contact versus regional metamorphism. All right, so I have a couple of different slides describing this. We'll just go ahead and narrate this one. So there's more than 2 metamorphic settings, but there's only 2 that we are going to consider for our second exam. Contact metamorphism or regional metamorphism. Contact metamorphism, sometimes called thermal metamorphism. This is going to occur when there is a magma chamber nearby. All right, so the rock doesn't have to be buried to a very great depth to metamorphose if there's a magma chamber nearby, because there's enough heat to cause it to change. Regional metamorphism, however, this is metamorphism on a much larger scale, and you do not have to have a magma chamber nearby, but this is going to occur in mountain ranges. So directed pressures and high temperatures during mountain building events, and certainly that last bullet there is true. Regional metamorphism produces the greatest volume of metamorphic rock on the planet. Every mountain range on planet Earth is going to have metamorphic rocks in it. At depth, of course, but sometimes, if you're lucky, due to tectonic processes and weathering, you might have that old metamorphic rock actually exposed at the surface on the side of the road. Okay, so we already discussed contact metamorphism, but just know that, well, let's write down the second bullet here. Okay, what's cool about this, again, is that contact metamorphism will produce metamorphism at relatively shallow depths. So you have high heat because there's a magma chamber nearby, but there's not much pressure. And what's neat is that this is going to produce something called a contact areal. In other words, it's going to produce this zone of contact metamorphism around that magma body. We'll look at a couple of drawings of that. Here's a drawing. So here you have an active magma chamber. Notice it's still orange. It's fueling an active volcano. You have rock layers in the background there. They're probably alternating sedimentary rocks, and some of them might be extrusive igneous rocks from past eruptions. And then notice that in between, in that sort of baby aspirin orange color, that's your zone of contact metamorphism. So those rocks that are closest to the magma chamber are going to metamorphose and change. This is a nice before and after image here. In the top left is before, when you have the right kind of plate boundary that's going to produce magma, and you have an active magma chamber, and you are metamorphosing that rock there in purple. And then on the bottom right is what it could look like millions of years later. Perhaps the tectonic regime here has changed, and now this system is extinct. So what you have there is a solid pluton, perhaps that is granite or diorite, that's shown in gray. You have your host rock, or the rock that was already in place there, and then in purple in between, that is your zone of contact metamorphism. Now here we have in the bottom right a real world image in a mountain range somewhere. And below you see that light colored rock, that is granite, that is an igneous pluton exposed. But what you still have on the top that has not weathered away is you have the contact metamorphism, metamorphic rocks there that are part of the metamorphic areal. So we don't have time for these other metamorphic settings, and that's okay. I'm just going to point out a couple of things. That image there on the bottom left, that is along a mid-ocean ridge, and that is a black smoke or a volcanic vent. So are you getting some low-grade metamorphism occurring along the mid-ocean ridges, including the mid-Atlantic ridge? And the answer is yes, because you have high heat there, because remember, those are active underwater volcanoes. And then the image there on the right, which national park? Is that going to be? Yep, you guessed it, that's Yellowstone. Okay, I don't know if that's Old Faithful. There are many geysers in Yellowstone. Anyway, that is some geyser in Yellowstone, and that's proof of volcanic activity because it's a hotspot volcano there, a mantle plume. And is metamorphism also going on? Contact metamorphism? Absolutely. Okay, so just a little bit more about the regional metamorphism here. Again, this is on a large scale, very large scale, and it has to do with plate tectonics, and it has to do with mountain building, things that are going on at our various convergent boundaries. We'll leave that alone. This is a nice drawing showing regional metamorphism occurring. So this is a particular type of plate boundary that later on we will describe as an ocean to continent subduction zone. You have an oceanic plate sinking beneath the thicker, less dense continental plate. And you are going to squeeze the crust and you're going to build mountains and create folds and faults. And you see there that towards the top of the mountain range, low temperature and low pressure. As you get deeper depth within that mountain root, higher temperature and pressure. And if this is a subduction zone, then yes, you're also going to form melt, and you're going to have magma chambers, and you're also going to have contact metamorphism. So in this drawing, we're seeing both. We're seeing both regional metamorphism and contact metamorphism occurring. This is a really neat image here because this is actually representing building the Himalayas. Something we'll get into more in plate tectonics, which we will begin after the second exam. Anyway, so the image on top labeled A is very early in the formation of the Himalayas, where you still had some oceanic plate there in front that was subducting. So that would be the Indian plate on the left and the Eurasian plate on the right. And then at time B later on, well, that oceanic plate has been consumed. It might even detach and make its way to the core mantle boundary, and we would now consider that to be a continent-to-continent collision zone. And in either case, you're going to get metamorphism. This is kind of neat because this is just showing the different steps in taking a shale and forming these 4 common metamorphic rocks from it. And it's showing you that, you know, in your more shallow reaches, it doesn't take much burial for shale to become slate, low-grade metamorphic rock. If it's buried further still, it'll become phyllite. If it's buried further still, then mica schist. And if it's buried to a deeper depth, it will become banded gneiss. So you might think that all banded gneiss is deep within mountain roots and that none of it's at the surface, but that's not correct because, well, our planet it's been around for a while, 4.56 billion years, and there are places where old banded gneiss has actually made it up to the surface. All right, these are some of our other metamorphic settings that we don't really have time for, except for the last bullet there. I do want you to write down the last bullet. Shock metamorphism. This is really cool. So we say that generally metamorphism is occurring in the lower portions of the crust. That's where metamorphic rocks are forming. But there is a really cool exception that occurs at the surface, and that is shock metamorphism, and that is only occurring when you have meteorite impacts. So the meteorite coming in, well, what are they called when they're out there in that belt between Mars and Jupiter? The asteroid belt. When they are coming towards Earth and entering our atmosphere, then they are meteors. If they can make their way through the atmosphere without completely burning up, then they are meteorites. So meteorite impacts, is that meteorites coming in? There's a tremendous amount of kinetic energy involved, and when it hits, boy, it releases a lot of energy, and it can cause shock metamorphism. And how do we know when it's happened? Well, in the past, how do we know when it's happened in the past in a particular location? If we find coesite, which is a polymorph of quartz or a shocked quartz, then we know that the only reason it would be there would be because of a meteorite impact. How else would we know that we've had a meteorite impact? Well, if the crater it created is still there. Okay, so this is Meteor Crater in Winslow, Arizona. And I think it's around 35,000 years old. So it's relatively young. And this is Arizona. This is part of the desert Southwest. So you don't have quite as much rainfall as we do here in the eastern seaboard. So the weathering processes are slower. So this crater is still here for people to go and study or just look at for enjoyment. I have to admit, I really want to go there. I forget how wide across this crater is, but I believe the size of the meteorite that hit, it wasn't super huge. Okay, it was smaller than the size of a house, maybe the size of a refrigerator. So the meteorite will make a crater that is much, much bigger than the meteorite itself. Not only do we have the crater here still visible, but we're going to find coesite there as well. And why do they call it meteor crater instead of meteorite crater? I don't know. Perhaps they did not consult a scientist. This is just kind of neat here. So on the image on the top left, that is a banded gneiss that had a shale parent rock, and you see a nice big garnet crystal there on the left, and some kind of coin on the right for scale. In the bottom right, notice that rock is kind of greenish black. That is not algae growing on it. That is metabasalt, which is a slightly metamorphosed basalt, and that's going to occur as a result of very low grade metamorphism along the mid-ocean ridges. Okay, we're coming towards the end of our unit here, and that's good because when we go over an hour, it just takes even longer to upload this to YouTube and have it process. All right, so what we're looking at in the top left there is a really nice image of a coesite sample. Wow, I wish I had that in my collection. Anyway, it doesn't look quite like quartz in any other way. And you don't have to have big samples of coesite. You can just gather sediment samples in these areas where you think maybe there was an impact, and you can study them with a petrographic microscope. And if you find coesite, shocked quartz, then you know you had an impact there in the past. So the map on the right is showing known impact sites here in North America and Central America. You know, is this an exhaustive list? Not necessarily. Might there be other sites we haven't discovered yet? Absolutely. We've been hit plenty. Okay, the good news is that there's less material near the Earth these days to hit us as there was earlier in Earth's history. So I'm going to point out, I don't even know that meteor crater is on here. That's a really good question. Not sure. If so, it's listed as something else, like Behringer. I'll have to look into that. Anyway, the one there on the Chesapeake Bay, that is a relatively recent discovery, and back in 2003 to 2006 is when I was a grad student at UNCW. At that time, now nearly 20 years ago, or 15 years ago, the USGS was drilling into that impact crater, and it is just offshore in the Chesapeake Bay, and they were studying it. We haven't known about that one forever. The most famous one on here that you may have heard of, I want you to look down there in Central America. There in the Yucatan Peninsula, they call that Chicxulub, and it's just offshore, the crater there. So that is a very famous crater, and I'll give you a hint. It occurred at roughly 65 million years ago. Okay, so why would that be famous? Might that be the impact that helped to kill the dinosaurs? Yes. So I don't remember when we'll see the iridium layer, if it's going to be in this unit or an upcoming unit, but I'll go ahead and mention it now. So there is an iridium layer that's found in many different parts of the world, and it's found in the stratigraphic record at about 65 million years. And iridium is an element, and it's very rare, and you don't find it concentrated in a layer the thickness of an ink pen unless you've had some kind of large meteorite impact. So we had known for a long time that we did not find any dinosaur fossils in rocks younger than 65 million years. We've known that for quite a while. And then we discovered the iridium layer in many places, and we figured there had to be a correlation there that, might the impact that caused the iridium layer have had something to do with the dinosaurs going extinct. I think we found the iridium layer in about 1980, and it took a good 10 years. It was about 1990 before we found the impact crater, which is at Chicxulub. Okay, so why did it take so long to find? Well, it is actually offshore. Oh, by the way, that wasn't the only thing that killed off the dinosaurs. At the same time, roughly 65, 66 million years ago, there were also flood basalts erupting in what is today India. So we think it was a combination of those two events that spelled the end of the dinosaurs. But you know what? That's okay. Because when the dinosaurs went away, that opened up new niches for mammals to then rule the planet as we do today. Although maybe it's bacteria and viruses that rule the planet. I'm not sure anymore. So this is our next to last topic for this unit. How do you bring metamorphic rocks to the surface? This process is referred to as exhumation. So metamorphic rocks form in the lower portions of the crust, but they don't necessarily stay there. Here and there we do have some examples where we can find metamorphic rocks, even very old ones, at Earth's surface, like on the side of a road through the mountains. 3 ways for this to happen. Okay, so the first one there is tectonic uplift. We will learn about tectonic uplift when we get to plate tectonics, which will be after our second exam. And let's say you take 2 continents and you smack them into each other. What are you going to do? You're going to uplift the crust, and you're going to build these tall, thick mountains. So in doing that, you're going to bring metamorphic rock that was at lower depths, you're going to bring it closer to the surface, where then bullet number 3 can help, and that is, of course, erosion. Of course, erosion is part of why we might see metamorphic rocks at the surface, simply taking away the material that's on top. All right, the one in the middle is a little harder to describe, and if we have time, there's a drawing I like to put on the board to try and imagine this. So what we're going to do is imagine that you have a piece of saltwater taffy. Why saltwater taffy? We need something that is maybe in a rectangle shape and that is pliable. We can stretch it. And we're not going to eat this saltwater taffy. I'm going to have you take a Sharpie and cover or color. On one side, you're going to color maybe like the bottom 3/4 of that taffy with a black ink. And we're going to say that that dark part is the metamorphic rocks in the lower crust. Then you're going to take your fingers on either hand and put them on the end of that taffy, and you're gently going to pull it apart and stretch it. Oh, and we need to measure the thickness. Before we stretch the taffy, we're going to measure the thickness of what's on top. The part we did not color is going to be our upper portion of the crust, sedimentary rocks. So now we're going to gently pull that taffy and stretch it. And after we stretch it a bit, you're going to go back in and you're going to measure. And that material on top that's representing the upper crust or the sedimentary rocks is thinner. So crustal thinning, stretching, will actually help to bring older, lower crust materials closer to the surface. And here's all that stuff about the iridium layer, but we've already mentioned it, but you can always pause here and read through that if you want. I have to admit it would have been a lot of fun to be involved in trying to discover this stuff and figure it all out. I was not a geologist yet. I think this is our last topic. So, continental shield. What is a continental shield? A continental shield is somewhere where you have large expanses of older Precambrian basement rock, metamorphic rock, exposed at the surface. Where can we find that? In Canada. So in Canada, we find that oldest continental crust, oldest North American material. We call that the Canadian Shield. Now, do we have any of that rock in the United States? Yes, we do. But the problem here is that it's covered by younger rocks and sediments. So what is so different about Canada? Well, Canada's further north, and the glaciation and the various ice ages was more intense. So glaciers are very good at taking away sediments and soil and sedimentary rocks and upper crust material and just kind of scraping all that away and exposing the old Precambrian basement rock. So I will ask you on your second exam to give me an example of where we find this older Precambrian basement rock exposed at the surface, and the answer is Canadian Shield, or you can just say Canada. So on the left there is a map of, and it's not all of Canada, it's basically the eastern half, almost 2/3 of Canada is where you're going to likely find places where you have this old basement rock exposed. So again, you see not so much down there in the United States, maybe a little bit to the east of, is that Lake Erie? I think it is. So that image on the right is likely taken from one of the Great Lakes, and it's just showing you where we have some of that Canadian Shield exposed at the surface.